All right, welcome to Co-21A. Welcome to those of you on Zoom. Hopefully you can see all right. Welcome to those of you in class. We're going to go over a few logistical things, but we'll get into some math for sure. We got a lot of time in this class, right? We meet Tuesday, Thursday from 10 to 11:50. That is a not insignificant amount of time. We'll probably take a break somewhere in the middle because I will need to pee most likely. You are also all welcome to use the restroom whenever you want, but we will take a break somewhere around 11 o'clock-ish. So you can, if you're thinking I need to go to the bathroom, but you're like, I know we're gonna take a break, you can wait for the break or you can go, whatever, I don't care. You're welcome to use the restroom anytime you want. Let's see. I wanted to ask, whose 21A classes are you in? And I know there's quite a few 21A instructors. So let me go look them up before I just have people yell out names. Math, that UC Davis, you. 1 second. And for those of you on Zoom, if you could type in the chat who your professor is, or your instructor is, I would love to know, just because it helps me kind of, I'm trying to be on all of their Canvas pages. I'm not yet, because some of them haven't responded to me, but just to kind of know what each class is doing. If none of you are in one professor's class, I kind of ignore what they're doing. So it helps me just better try to tailor what we're doing in here. So let me go ahead and look at who's teaching. I've emailed them all. I don't remember who all of them are, to be honest. Let's see. So raise your hand or type in the chat if you have 21 names. Come on. Let's see if you have Eli Moore as your professor or instructor. Eli Moore, anyone? Okay. Someone on the Zoom, cool. How about Christopher Hegerid? Okay. How about Janko Grosvenor? Professor Grosvenor, all right. I had him as a professor many years ago for an upper division math class, yeah. I went to school here in case that was not clear by my previous statement. I graduated with a degree in math many years ago. Let's see, who else have we got? Karana Burke, Professor Burke, okay, one person. All right, how about Dr. Haas, Joel Haas? Cool, yep, all right. A couple people on Zoom. Let's see who else. Joseph Turan, okay, a few of you. Anna Parlak, one of you, anyone on Zoom, okay. All right, and I think that's it, that's everyone. Okay, so this is like the majority of you are in Dr. Haas and Dr. Grosvenor's class and a couple other things. All right, good to know. I mean, it honestly probably won't change that much what I'm doing, but it's kind of like if something's going on in their class or they've not something, it's good to be aware of. There's the link to the attendance form, or I should say the QR code you can scan to get to the attendance form. I also emailed you all the links, so if you're having trouble scanning that for whatever reason, you can check your email from there. I guess that's kind of the most important logistical aspect of this class is that I do need you all to fill out the attendance form every time you come, or every time you come via Zoom, or if you don't come to class and you watch the video later, I would still like to count your attendance because, well, if you're registered for the class, that is the way you pass the class, by attending. So whether you're attending live, or I should say in person, or live, or watching a video later on, please do record your attendance because I'm going to go put it in Canvas later on. And that is literally the basis for how you pass this class if you're registered for the class. If you're not registered, which is also totally fine, right? If you sent me an email or you filled out the form on our website to be added to Canvas, but not registered for the class, your attendance is not important in a passing the class sort of way, but your attendance, as you might have read on the form you just all filled out, you might have read that some of our funding for the AATC comes from the students we serve. And so the more numbers we have showing that we are serving students, the better it is for our department. So if you could please fill out that form whenever you attend or whatever, you'd be doing me a great favor. And I need you to, so please do it. Hopefully, yeah, cool. All right. What else? Let's go ahead and look at Canvas for just a moment. And also, I should say, like, a fairly easygoing guide. Please ask questions if you've got them. I'll try to cover the important things. If there's something I'm missing, if I'm making a mistake, speak up. I'm very open to feedback. Yeah, that's it. So let's see here. Let me see. I need to press the button over here. I think. Let's see. Let's make Sorry, there's always so many things going on over here. Let's do that. The right button. Oh, it is. Find out in a second. Oh, yep. Oh, yeah. We got to do this whole. Yeah, it's always super fun. Let me try doing something I tried last time that did not go well. I'm going to try it this time. Hopefully it goes well. Let's see here. Because it's hard to like see what's going on over there when I move things over there. So I'm going to try and mirror my screen instead of extending it. The last time it ended up not being great. So okay, let's go. Let's do it. All right. Last time it looked like garbage. Like it turned purple. I think I jiggled the cord or something. Good. Okay, great. You can see the things. Awesome. Those of you on Zoom, just a second. Let me show you the things as well. Cool. Share the screen. Yeah. Right on. Okay. I think we're good to go. I don't really need this though. Okay. We'll come back to the faces later on, but you don't need to see the faces right now because it's talking about the Zoom. It's not the best. It could be. I'd love this to be not in the way. Okay, that's as not in the way as it gets. Welcome to class. Have a seat. We're just talking about the logistics, and as I was saying to everyone else, which I'll put back in a moment. When you have a chance, please do fill out the attendance form. But let's talk about what's on Canvas. There's not a whole lot on Canvas, and I do plan on moving some things around eventually. Let's go ahead and look at home, which I think is the same as the syllabus. Yeah, it is. As far as this class goes, the idea is we're going to talk about 21A. I'm going to do some examples. I'll do lots of examples. That's probably most of what we'll do. And sometimes I'll have you work with each other. It's kind of, we're still in this kind of hybrid thing where the people on Zoom can't really work with other. I mean, we could do a breakout room, but nobody likes breakout rooms. It's kind of not the best. But I will most possibly, likely, I don't know, have you all work together at some point, at least work individually on problems. I will have you at home work on stuff too. I'll be like, do this problem. And I'll be like, I'll wait here for a few minutes and they'll do the problem. We'll talk about it. I will say, as far as for the people on Zoom, I'm definitely more focused on the people in the classroom. So when we are working on problems, I'll probably be looking at what they're doing, whereas I can't really see what you do there. I might occasionally ask people on Zoom for, to type your answer in the chat or something like that. But it is a better in-person experience. So if you want to come in person, I highly recommend it. But if you want to not come in person, then it's also totally fine. So that's also true for all of you. You're all welcome to come via Zoom if you prefer. I highly recommend coming via Zoom if you are not feeling well. So yeah, there's that. Welcome to class. Let's see. So let's see what's on here. Let's just go through it real quickly. So how can you reach me? Email is best. Specifically, not the Canvas inbox email tool, because I get a bajillion emails from Canvas, and so I have them go to another folder, and so the ones from students also go there, and I kind of miss them. Sometimes I go look, I'm like, oh, there was a thing I should have responded to like a week ago. The better way to get hold of me is just to send me an email directly to my email address, jjparmenter@davis.edu. You can also, if you want to see me for to talk about math, you can make an appointment with me on Calendly. I think currently I don't have any appointments available because of how my calendar is set up, but that will change next week. So you can certainly make an appointment with me for, I think, a 40-minute appointment is how long I've decided they should be. And this is less than ideal up here. Less than ideal everywhere I put it. It's fine. You can also call my office phone, which feels like the weirdest choice option available, but you could do that if you wanted to. As far as how to see me in person, if you want to get more help with math, I am in lots of places. I'm in lots of places. So Mondays and Wednesdays from 11 to noon, I'm in C class, which is the Center for Chicana Latinx Academic Student Success. It is located on the second floor of the Memorial Union. That's if you're over by the coffee house and you go up those outside stairs, if you just veer slightly to the left after you go up them, that's where C class is. I'm in there Monday and Wednesday from 11 noon. You can also find other math specialists like Grant, I think Sarah, in there occasionally as well. I don't know what their hours are, but they're probably posted on our website, which you should all be familiar with. If you're not, it's tutoring.ucdavis.edu. Math. And all sorts of lovely information. I'm curious, are our hours on there? Also, while we're here, math drop-in, Monday through Thursday, 10 to 5, Friday, 10 to 1, Sunday, 3 to 7. That's in the lower level of the library. that is probably the first, if you were looking to get math help, that is the first place I would go, because that's where there's the most like time availability. And sometimes we are the math, but that's run by student tutors mostly. Sometimes myself, Grant, Sarah. Claire is virtual, so she won't be there. There's one other person I'm not thinking of. Oh, well, I'll figure it out. Oh, there we go. Yeah. Oh yeah, it does have, cool. It does have math stars on there. Awesome. So you can see right here where to find us. You can find me Monday, Wednesday, 11 to 12 in C class, Tuesday, Thursday, Friday in CADS, which is the Center for African Diaspora Student Success, which is in the, I need to find out where it is. It's in the South Silo building on the second floor. And then actually this does not have my, I'll have to have Sarah update that. This does not have my in drop. I don't think we have drop-in on here, I guess. I'm also in the drop-in room on Mondays and Wednesdays from 3 to 4. So this is where you can find me. You can find other people too. Yeah, I'm moderately available. I'll probably be late to these 3 to 4 office hours because I teach a class every day right before it. And it's a little bit of a walk, but I'll be there eventually. About this class, I'm just kind of looking through here. There's like stuff to read if you wanted to read it. Our class is now, you are here. Congratulations. What else? Sorry, I'm a little. Come to class prepared to do math. You should all have something to write on and write with. Tablets are great. Paper and pencil, also wonderful. If there's something I can do to make this class better, you should let me know. I do make mistakes, by the way. Like, you should definitely let me know if I'm saying something, doing something terrible. I'm writing a minus sign when it should be a plus sign. If I said 3 squared was 6 when it should have been 9. Sometimes those kind of things happen. Just be like, hey, James, yeah. Zoom, I think we know how to use the Zoom at this point, but if you have Zoom questions or concerns, you're welcome to ask. Again, I should say, you are welcome to come via Zoom if you want to. I recommend coming in person because I think you get a better experience, but sometimes the Zoom is ideal. Or maybe the weather, I mean, not that we're expecting rain anytime soon again, but maybe the weather is terrible. Like, I really don't want to go out in that. So apparently in this last like rain system we had, Woodland got like the most rain of anywhere in California, which is kind of great. Just interesting fact. Let's see. Attendance, I talked about attendance, we'll talk about it again. So here's the form for attendance. It should look like that. You all got emailed with an email with that link like a few minutes ago. So if you haven't filled it out yet, I encourage you to go look at your email and fill it out. If you're absent from class, you can always make up that absence by watching the video of class, which I will record, which I am recording right now, and I'll post later. I'll try to edit it out at the beginning and the end, but I don't do a whole lot of editing. You're certainly welcome to watch. By the way, you can watch it like sped up, right? Like, you don't have to watch it at 1. You can watch it 1.5 times or 2 times, which is definitely, I think 1.5 is a sweet spot. 2 times is a little too fast because although there were definitely, so last beginning of the 2020, when I was watching professors teaching their classes, some of them were really slow. It's like double time was the way to go. Like, this guy is, I was really like, good pacing at double time. But I think sometimes I talk too fast for that. So as far as passing the class, you just have to come. I think a passing grade, yes, I've written a passing grade is 75%, meaning you have to come 75% of the time. Then, I mean, you should participate, right? It shouldn't just be like come and fall asleep. Although if you really need to sleep, I understand. What else? Videos, yeah. Some notes. Sure, the class is. So just as a reminder, this class counts for 1. If you're registered for the class, it counts for 1 workload unit, which means it counts towards being a full-time student. It counts towards financial aid purposes. It does not count towards graduation, which is totally fine. You will have way more units than you need to graduate by the time you're done at UC Davis. It's kind of unavoidable. But yeah, so if you're registered for this class and you didn't pass this class, it wouldn't really matter, unless you absolutely needed the class to meet the minimum number of units you need for the quarter. So if that is the situation that you are in, you definitely make sure you pass this class. Other than that, it's like not passing this class. I think it shows up on your transcript, but it doesn't really affect anything else at all. So if you didn't pass this class, it would not be the end of the world, although it is super easy to pass. So you should all pass if you're registered for it. What else? You might be spending a lot of time doing math this quarter because it requires a lot of time and thought. I feel like this feels like too much, but I guess it's probably not. It says successful students are usually spending 10 to 20 hours per week outside of class doing homework. That seems like 20 seems like a lot. 10 seems, I guess I was doing a lot. So I took this class, not this class. I took 21A when I was a student here. Okay, I'll date myself. Back in 1998, many years ago, I took 21A, and I guess I was doing 5 hours in a kind of co-classy thing like you guys are doing, although it was a different class. And then, yeah, I guess at least 10 hours a week is probably pretty reasonable. So, yep, be prepared to do a lot of math. And then, yeah, there's all this. Okay, let's look at the modules. I feel like my modules are not very up to date, but maybe there's a link to the class attendance form, Grant's website, which is always a good source of all things UC Davis Mathy. You can see all sorts of lovely things here. We'll talk about these problem solving things in a moment. And then I've also have these sheets here are the same as these things here. They're just laid out better on Grant's website. And then, so yeah, the derivative worksheet, we'll get there eventually. That's, yeah, sure. And some useful handouts. Yeah, right on. Okay. Yeah. So there's some stuff you can't see on the modules yet. I can see it right now. But if you look here, you won't see any of this because I haven't published it yet because we're not close to the final exam. Don't sweat it. I think there's no assignments. That's not true. There's one assignment. The assignment is attendance. I guess I'll try to update, I'll try to record your attendance relatively frequently so that you can see how you are doing attendance wise. So, questions, comments, observations? Yeah.
Oh, wait, so the main purpose of this class is just to prepare for placement exam next quarter.
I wouldn't say, well, so no, I would definitely not say that. The main purpose of this class is to be a supplement to Math 21A. So this class is intended for students that are enrolled in Math 21A. Yes. Sorry, in the back first.
Is Math 21A more like AB or like BC, or is it a combination?
It's more like AB. So the contents of 21A, I would say we're going to talk about limits, derivatives, finding maxes and mins of functions, graphing, some optimization, some related rates, implicit differentiation. That's about it. We definitely don't. So we don't get to the fundamental theorem of calculus. We don't talk about integration at all. None of that. That's all in the second quarter of calculus. That answer your question pretty well? I don't know the BC material perfectly well because I didn't take it. I took AB when I was in high school again many years ago. So and I always remember being surprised that there was implicit differentiation on the AB test because my teacher said there wouldn't be, but there was. So yeah, yes.
Yeah. Is this going to be a type of class where we kind of just do practice problems over and over again, or are we going to be working on homework and answering? We're not. So I would say we don't. In fact, sorry. Let me for just 1 second for the people on Zoom. Let me turn back on the so you can see me. Not that it's super important to see me, but it feels weird just to be like, especially when I post the video later. I'm like, oh, you can't see it. You see just voiceover screen. It always feels weird to me. So let me do this. Let me do that. Let me do that. Okay, fine. And let me do that. Yeah. So if you haven't filled out the attendance form yet, you can screenshot that and it'll take you to the right site. And those of you on Zoom, you can see me now. Yes, no, maybe so. Anyone? Sorry, I'm going to answer your question, but yeah, okay, cool. Awesome. Cool. All right. So I would say we generally don't work on homework problems, although I'm not averse to that because you can find the answer to any homework problem really anywhere. Generally, what I would say this class consists of is me kind of doing some instruction. So like talking about maybe what you're going to be talking about for the week. Like my plan for today, well, actually my plan is kind of all over the place because there's so many like building up to before calculus stuff that people are like, yeah, we're just going to assume you all know all the pre-calculus things all the time, even though that might not be true. So the plan for today is to talk about some of the pre-calculus things and also to have you potentially definitely work on problems. So like I'll do a couple examples. I'll be like, okay, now I'm going to have you guys try this one.
or maybe I'm going to give you all a handout and you're going to work in groups together. So that's kind of the general vibe of this class, is that we are doing lots of practice. I'm giving you some examples, some instruction. I would say it's mostly like that. And then, but yes, like if there is a homework problem, you're like, we have this homework problem, I don't really know what's going on, I'm happy to look at it, happy to work on it, happy to do one similar. Yeah. I imagine most of you are doing homework via some sort of web work or WebAssign, or which are great. Like, I mean, they're very good in that they allow you to do problems and know if you're doing them correctly or incorrectly. They can be kind of finicky sometimes. Definitely many times with students, we have had the right answer, but we've been inputting it in some incorrect way. So definitely it takes a little bit of practice getting used to making sure you're writing things or typing things in there in the correct way. Yeah, you got a question?
So when are your office hours /
That is a good question. I would have said today, but I have getting my second booster shot during when I would have had office hours this afternoon. So not today, but I do plan on being in my, I think I only have one office hour tomorrow from 3 to 4. I do plan on going over to CADS tomorrow to visit the place and also to be in office hours tomorrow if they're open. I think they're open, but definitely next week and tomorrow.
For each of the number of problem solving sheets for each different class?
That's a good question. So I would say those problem solving sheets have been around for many years. Like, I think those were the problem solving sheets we might have had when I was a student. They were written, and we've updated them a little bit, but I would say they're used more as a guide. So I will not, and they're definitely not, I would say I will sometimes have you work from them. I will sometimes not. It kind of depends. But the intention is not specifically that we're just gonna, I don't know. I mean, I posted them there to have as a resource. I should also post the solutions there because it'd be good to have the solutions. I've done a thing and now I can't undo it, and it's kind of killing me. 1 second. Oh, there we go. Okay, great. Sorry, this screen, the screen is just not doing what I want it to. It's very annoying. Sorry. Oh well, I'm stuck with it now. Okay. Let me look at one more thing here. Yeah. I mean, I think working on the problem solving sheets is good. Oh, that one, those are, that one looks a little bit different than the ones I have on Grant's website. Good to know. I'm going to take a look at those, not today, well, maybe today, see if they're the ones I really want up there. But I would say they're definitely a good source of problems to work on. I imagine you all have a fair amount of homework problems to work on as well, right? Like you have homework to do. And I feel like, well, so I was looking at a couple of them. I think someone has like that's what I'm looking for, a how to use web work sort of assignment. Like I think Dr. Burke, she has an assignment up that's like mostly just problems about making sure you're entering things into web work correctly. In fact, let's see, let me take a look at it here. Yeah, her first assignment is mostly kind of just how to write things out. Yeah. Okay, no, I mean, maybe half of it, and then the rest of it's kind of like some pre-calculus problems, like, is this an even or odd function? This kind of thing. All right, yeah. Okay. Other questions? They're asking good questions. I appreciate all the questions. Any questions from the Zoom folks? Also, for those of you on Zoom, you are certainly welcome if you want to ask a question using words from your mouth. You can unmute yourself and say words. You can also type in the chat. I try to keep an eye on the chat, but often my focus is kind of that way, so I might not see what's going on over here necessarily. I really want to make this box a little bit smaller, but I can't seem to do so. It's kind of killing me. Oh, almost there, 1 sec. Sorry, I know it's not super important, but there we go. Got it. Much better. Okay, excellent. All right, so I used to like writing on the chalkboard in this classroom, but it doesn't really work for the people on Zoom. So we will not be writing. What? Why? Okay, sorry. There things are popping up and it's terrible. There's just like, why would I ever open Microsoft Edge? You gotta be kidding me. Go away. Okay, sorry. So things are just opening for some reason. I have no idea why. I guess we could do some math. So I imagine all of you had class yesterday, like 21A yesterday. For whoever your professor was, I imagine you probably didn't do a whole lot other than talk about class logistics. Maybe somebody tried to do a little bit of math, maybe not. Some people did. Okay. So let me take a look. So here's what I would say. A lot of your professors, not all of them, some of them are more realistic than others. A lot of them are going to assume that everything in chapter 1 is like, you are supposed to know all the things in chapter 1. And just to read you the titles of the things in chapter 1, we have functions and graphs, combining functions and shifting, trigonometry, exponential functions, inverses, and logarithms. All that's like we're supposed to know. So it feels like today would probably be somewhat well spent kind of giving an overview of those things, which I know is kind of, I mean, it's literally kind of like all precalculus. Chapter 1, all precalculus. Or at least all the stuff we think is going to be stuff we need for precalculus. Oh, I should not really. Sure. Functions. There's just so much to talk about. So let's talk about functions and their graphs. Okay, let's kind of start. So there's so many functions, right? What is a function? A function is a rule. So for example, you could have f of x equal to x squared. That's the function. The brightness there could be a little brighter. A little better, right? Yeah, that's a little better. Let me do one thing. Better? Yeah? Okay. So a function is a rule. That assigns exactly one output to each input. So you put in the value for x, you get out a value for f of x or for y. In this function, we can find a few values. F of 3 is 9, f of 4 is 16, f of negative 4 is also 16. It's okay if the outputs are the same, but the inputs, right? One input can't give you two different outputs. So this is a function. Its domain. We'll talk about domain a little bit more in just a second here. Domain is everything, right? There aren't any values of x that you cannot put into this function. So the domain we can either write as the fancy R for all real numbers, or you can do everything from negative infinity to infinity. Either way. I like this because it's less writing, but this is probably a little more standard. The range, on the other hand, is always kind of interesting. The range is all the possible output values. For this function, the lowest output value we can get is 0. You can't get a more lower value. That's not very. You can't get a lesser value than 0 from this function, but you can get 0. If you input 0, you get out 0, and then you can get any positive number you want. So the range is all non-negative numbers here. Something else I want to say about this. On the other hand, something like this, y equal to plus or minus the square root of x, is not a function. Even though it comes up sometimes. Not a function because if you input one x value, you get out two different y values. So for example, if you let x equal to 25, you get y equal to 2 different values, plus or minus 5. Not a function. Let's look at their graphs. This is where I always kind of like try to keep kind of the previous stuff on there and still go up. Also, oh, that's the other thing I should say. If I'm ever writing something, you're like, I can't see that, James, just say, James, I can't see that, because sometimes I'm like, oh yeah, I did okay. So that, I mean, I know it's right there. I should be able to see it there, but like sometimes I forget to look there. I'm so involved here. So please do let me know if you can't see a thing. It's not a big deal, but it is a big deal because you need to be able to see the things. So for f of x equal to x squared, the graph is your standard parabola. Vertex at the origin, looks nice. We can plot some points. No one wants to plot any points. For y equal to plus or minus the square root of x, well, I should point out, these are kind of inverse relationships, right? If you wanted to quote unquote find the inverse function from f of x equal to x squared, the process for finding the inverse function is to write y equal to x squared, then to switch x and y. So you have x equal to y squared, and then to solve for y. When you solve for y, you get y equal to plus or minus the square root of x. And that's kind of the issue here, in that if you try to graph this, I mean, we can graph it. It's not that we're going to fail to graph it. Here is y equal to the positive square root of x. And here is y equal to the negative square root of x. It's not a function. Why isn't it a function? Yeah, 2 outputs. What's another way I could say that? It doesn't pass the right, it doesn't pass the vertical line, which literally means the same thing, right? Not passing the vertical line test. Right, this vertical line hits that graph in 2 points. Exactly means that for this x input, let's say that's x equal to 25, there are 2 different y outputs.
Are you saying there's always rotating 90 degrees?
No, so it's not a rotation of 90 degrees, although it does look like that here.
So this is just for his graph.
Right. Well, but there is a general rule. And the general rule for an inverse is that you're actually reflecting the graph across the line y equals x. So for example, yeah, that's a really good question. Let's look at another example. I think I'm done talking about this one. Yeah, sure. So let me try and keep my notes in order so that when I post them later on. Let's look at, we're just going to go everywhere today. Why not? So let's look at f of x equal to sine of x. Great trig function. When I'm graphing this trig function, these are the values I like to keep in mind. So when I'm graphing sine or cosine, I think of the quadrantal angles for x: 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians. They're called quadrantal angles because they're literally the angles that separate the quadrants. Right? 0 radians, pi over 2 radians, or 90 degrees. Hopefully you guys see me on Zoom, right? I'm like, yeah, I know it's always not the best. That's why you should come to class, because like you get to see me do this. And then pi radians is 180 degrees, and then 3 pi over 2 radians, and then right. Each of those quadrantal angles separates quadrant 4 from quadrant 1 from quadrant 2, 2 to 3, 3 to 4, and so on and so forth. Okay. Good old unit circle over here. I mean, this is like the abbreviated unit circle, which I, as my wife always says, terribly call the 4 corners of the circle. It's just the what? I'm going to say the 4 cardinal directions of the circle. No, I'm going to say the 4 corners of the circle. I know circles don't have corners, but I'm going to say it anyway. What sine is 0? So we definitely need to know how to find sine and cosine. So as a reminder, since we've already got that's not my best circle ever. Right. The sine is the y value. So if this is a unit circle where this is a radius of 1, and I drop a perpendicular, and that angle is theta, then sine of theta, well, actually, let's say that this length here is x, and this length here is y, this coordinate is x comma y, then sine of theta is definitely opposite of our hypotenuse. And what's cosine of theta going to be? Right, which in this case is just. And so then we can say, well, look, the coordinate on the circle, and this is the whole deal with the unit circle, right? The coordinate on the circle is the value of cosine and sine. And the way I remember which one is which is it's alphabetical. X comes before y, cosine comes before sine, right? Because c comes before s in the alphabet. So this point here is cosine of 0 radians comma sine of 0 radians. And I know what that point is. That point is 1 comma 0. Let me zoom in a little. Also, apologies in general for my less than excellent handwriting. It's mostly legible most of the time, but if you need clarification on something, I am not offended. I know what my writing looks like. So if you're like, James, what the heck does that say? Just ask me. This point up here is the point 0 comma 1 because we found 0 in the x direction and 1 in the y direction. Then over here we have -1, 0. And then over here 0, -1. And sine is the y coordinate. So sine of 0 radians is 0. And sine of pi over 2 radians is 1. You can't see I'm writing over here. Let me zoom back out. The manual zoom. All right. Let's refocus here. Okay. And then sine of pi is going to be 0. Sine of 3 pi over 2 is going to be -1. And sine of 2 pi is going to be 0 again. So our sine graph, at least one period of our sine graph, looks like this. No, come on. And so on. And then it just repeats. That's why it's called a periodic function, because it does the same thing over and over and go again each period length. Yeah. While we're here, might as well mention the domain of this function is everything. Right. There are no values you can't find sine of. I mean, sometimes some of them are more challenging. Like I don't know what sine of pi over 9 radians is, but it's findable. The range here, on the other hand, is quite limited. How high do we go? How low do we go? Right. This is actually a fact that comes up a lot, especially I'm sure your teacher at some point is going to talk, we'll talk about the squeeze theorem or the sandwich theorem. This piece of information that sine of x or cosine of x is always between -1 and 1 is often used when dealing with squeeze theorem or sandwich theorem problems. But the reason I mentioned this is because I wanted to talk about the inverse function and how it looks graphically. So when I'm thinking about an inverse function, so when we're finding an inverse function, we are literally interchanging the role of x and y. So that's all I'm going to do is I'm going to switch x and y. So instead of having of y equal to sine of x, now we're going to have x equal to sine of y, which is not going to be a function, right? Because what's going to happen is now the y values are going to be the angle parts and the x values are going to be like the output parts. So it's going to look like this graph, except it's going to be on the y-axis. So I should actually be very, very clear. It is a function if you change your perspective, right? If I write x equals sine of y, well, yeah, that's a function if I'm thinking of x as a function of y. But it's not a function in the standard typical sense where we're thinking of this being right, the x values being the inputs and the y values being the outputs. Question or is
it's a question. So how about when we restrict the domain?
well, that's what we're going to do. Yeah, that's definitely where we're going. Yes. But I wanted to point out first the graphical implications of what an inverse is. So all I'm literally going to do is I'm going to interchange my x and y coordinates. So instead of having 0, 0, I'll have 0, 0. Instead of having pi over 2 comma 1, I'm going to have 1 comma pi over 2. The graph's going to be a little bit tight, but it'll fit. So 0, 0, and then I'm going to have 1 comma pi over 2. And then instead of pi comma 0, I'm going to have 0 comma pi. Instead of 3 pi over 2 comma negative 1, I have negative 1 up, and I ran out of room. Such is life. Ooh, we'll do something fun. Okay. And then I'll also go down here. Instead of negative pi over 2 comma negative 1, I have negative 1 negative pi over 2. So graphing some of this, graphing it poorly. There's my not function, x equals sine of y. But what I want to emphasize here is that this graph is literally this graph reflected across the line y equals x. Right? If I, and sometimes it can be hard to visualize, but if I flip this about this line, I end up with that graph, and vice versa. And it's because we're really switching what x and y are, which is the same as flipping across the line y equals x. Also, if you're not great at graphing, which, you know, graphing can be difficult. There's this great tool that I imagine most of you are aware of, Desmos. I highly recommend becoming familiar with Desmos. It's just a great tool to see things. But if I want to graph, you know, y equals sine of x, great, there it is, looks beautiful. And if I want to graph x equals sine of y, I can also do that. How nice. And you can really see that they are kind of reflections of each other in the line y equals x. Yeah.
Is there a tool on this notation for rotation?
I am not sure. Although I would say, again, this isn't a rotation, this is a reflection.
Right.
But yeah, I don't know if there's a predefined way to rotate a graph on this.
There's a mathematical notation for rotation at all.
Well, I mean, yes, but it's kind of a linear algebra thing.
Okay, so it wouldn't be.
Yeah, not really. So I mean, yeah, I mean, really, the way you reflect the graph across the line y equals x is by interchanging y and x. So we are kind of doing it. This is the process, is by finding the inverse function. One other cool thing. Oh, well, we'll come back to that. So we would like this to be a function. So how do we make it a function? Well, most of the time we don't really care. Like if something like, for example, you know, back here, to make this inverse relationship a function, ooh, that's not what I wanted to do. You simply say, well, I'm going to restrict the domain of the original function so that it is a one-to-one function. So what we would do here is we would say, I'm going to restrict to just this. So if we look at just this portion of it, then the inverse part of it is just this part here. And that part is a function. So if you restrict your original function so that it's one-to-one, meaning that it passes the what test? That's the test to be a function. We want the test to be a one-to-one function, which means it has to pass the horizontal line test. So this function originally doesn't pass the horizontal line test, but if we cut this part off, it totally does. So really what you're doing when you're looking at the horizontal line test is you're looking at what the vertical line test would be for the inverse. So if you want this inverse to pass the vertical line test, you need this original thing to pass the horizontal line test. So if you cut this part off, you're cutting this part off, and then it totally does it. Same kind of thing for sine of x. I want sine of x to pass the horizontal line test. So I'm going to cut it off. I'm going to go just from here to there. And so then the inverse function, y equal to the inverse sine of x, or if you prefer, y equal to the arc sine of x. Those are both notations for the same thing. Is going to begin at negative pi over 2 comma negative 1, except it's negative 1 negative pi over 2, and end at, instead of pi over 2 comma 1, 1 comma pi over 2. It looks like this. It's kind of a weird function. It's got a very limited domain and range, but that's what it is. Okay, let's see. Sorry. Catalyst. Okay. What else to say? Let's talk about the other trig functions just for a second, because it seems like a good place to be.
So for the arc sine or arc cosine or arc tangent, all of that, we have the graph and we're trying to find the x value domain that's outside our domain and range. We just minus it by multiple of n pi, 2 n pi.
So, like, for example, if you were trying to find maybe say the arc sine of
3 pi over 2.
well, so I should say when you're talking about an inverse trig function, your inputs are not angles. So that's a kind of a good place to go. So for example, we know that sine of 3 pi over 2 is negative 1. When you so right, inverse functions, what do? They interchange the places of the inputs and the outputs. So for a sine function or any regular trig function, the input is what kind of thing? What are you taking sine of? An angle, right? We're taking sine of an angle or cosine of an angle, tangent of an angle. So for sine, cosine, and tangent, cotangent, cosecant, and secant, you're inputting an angle, you're getting out a value. For the inverse trig functions, you're doing the opposite thing. You're inputting the value and you're getting back the angle. So for example, if I wanted to find the arc sine of negative 1, this is where things get kind of stupid. What's the angle? So close. You're in the right spot, but the problem is, and I was hoping you would say 3 pi over 2. I definitely set you up for that one. Thank you. Thank you. The problem is the inverse sine function has a range that goes as low as negative pi over 2 and as high as pi over 2. 3 pi over 2 is too high. I need to go back the other way. So here it's going to be negative pi over 2.
And our domain itself is restricted to negative 1 to 1.
Right.
The radius can never be more than 1 being set.
Right. For sine, for inverse sine and inverse cosine. Just that's true.
Over tangent, it can be.
Tangent can be- so yeah, so I don't want to get too much down this particular rabbit hole because it's not super it's kind of very specific, but I would say we should definitely be aware of the trig functions. So just like we graphed sine, let's look at cosine and tangent for just one second. So for the graph of of cosine of x, it's going to look like the following. Again, I'm thinking of those 5 values. I may be, again, drawing my little unit circle with the 4 corners of the circle. Probably don't really need to draw those points in there, but you certainly can. And then the angles are 0, pi over 2, pi, 3 pi over 2. And if you've gone all the way around, right? Obviously, maybe not obviously, those angles could actually be anything, right? I could be writing, I can keep going. 5 pi over 2, 3 pi, 7 pi over 2, 4 pi, right? Just keep going round and round and round and keep getting angles that are bigger and bigger and bigger. But these are kind of the normal-ish ones that we usually write to get an idea of what's going on. Cosine of 0 is going to be 1. And then cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is back to 1. So the cosine graph looks a lot like the sine graph. In fact, they're pretty much the same graphs. They're just shifted horizontally from each other. That's maybe not my best cosine ever, but you get the idea. It looks like the cosine graph, kind of. And then we could also graph the inverse just for a moment here. Why not? if you want to graph the arc cosine of x or the inverse cosine of x, it looks like, well, you always have to make a choice when you're finding the inverse trig function. And this time we make the choice to go from here to there. So the inverse cosine graph looks kind of funky. Instead of 0, 1, we get 1, 0. And then we go all the way to, instead of pi negative 1 pi. It looks like this. There's your inverse cosine graph with a different range. Kind of weird. Again, I should point out, don't get too caught up with it. Like I got kind of on the tangent, but I couldn't help myself. But really, I would say don't worry so much about the inverse trig functions. Like they're certainly a thing we should be aware of, but they're not like the main focus of precalculus. They're a small sliver of precalculus. Let's graph tangent as well. So tangent's kind of funky. So tangent is sine over cosine. And so when I think about that, if I think back to my unit circle kind of deal, and I've drawn it like 3 times here. Sine over cosine is the y over x. That's an x, believe it or not. There, now it's an x. So, I'm sorry, I'm not looking for. Okay, sorry, I'm just trying to make sure I'm not ignoring the chat completely. Okay, let's see here. So sine over cosine, so y over x. So sine of tangent of 0 is 0 over 1, which is 0. And then tangent of pi over 2 is 1 over 0, which is undefined. At pi over 2, we get a vertical asymptote. Because what's really happening, if you think about as we travel along this unit circle in quadrant 1, what's happening as I go this way to the x values? Are they getting bigger or smaller? Sure, the slope is getting steeper. I would say that the x values are getting smaller and the y values are getting bigger, closer to 1. So my y over x is a fraction that is increasing, right? It's getting bigger and bigger and bigger. Specifically at, I should point out, at an angle of pi over 4, or 45 degrees, they're the same, right? Right, that's literally the line y equals x at a 45-degree angle. So at y equals x, we're going to get a value of 1 for tangent because sine and cosine are the same. So at pi over 4, we get a value of 1, which is a. But then as we continue onward towards that point there, towards the angle pi over 2, the fraction just gets bigger and bigger and bigger. Because if you have a denominator that's getting super duper small, you have a fraction or a ratio that's getting infinitely large. So what's going to happen is this is going to blow up. Like that. And then the same kind of thing, I'm going to go backwards kind of towards negative pi over 2. If we go this way around the unit circle, the same sort of thing is happening. X is getting smaller, closer and closer to 0. And the y values, or the y coordinates, getting closer and closer to -1. So we're getting, again, a very, very large fraction, except it's a negatively large fraction because the numerator is -1 and the denominator is a super small number. We're doing like this. And then it does the same thing over and over and over again, right? Over here, we're just going to repeat the same kind of behavior as we had over here. So it's going to look like this. And so on, and so on, and so on. So kind of differently than sine and cosine, tangent has a period that's just pi. The length of how long it takes for tangent to repeat itself is pi long. Whereas for sine and cosine, it's 2 pi long. Kind of interesting. The domain here is a little funky because we're missing all the odd multiples of pi over 2. Right? You can't have 1 pi over 2 or 3 pi over 2 or 5 pi over 2 or negative pi over 2. So the kind of fancy way of writing the domain here is to say, okay, I'm going to start with this middle part, which is negative pi over 2 to pi over 2. I'm gonna leave myself a little space, maybe a lot of space. I'm writing parentheses because I don't want to include those values. And then we're going to just say, well, I want that, and then I want to shift it over by how much? I was going to say just 1 pi, but yeah, in general, we want to be able to go over as many pi's as you want. So you say we're going to add, people either use k or n. The idea being that n is an integer. So that's how you write the domain of this. It's kind of super annoying, but it is what it is. You can also do it kind of the longer way to say, oh, it's negative pi over 2 to pi over 2, union pi over 2 to 3 pi over 2, union dot, 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 dot. That's another way you can kind of do it. The range here is everything. You get all possible numbers. Okay. Let's see. What else should we talk about? What else is on my list? Yeah, we should go back that way. Okay. Yeah, while we're at it, let's talk about even and odd functions. If this feels like it's kind of all over the place, it is. And that's because there's so much pre-calculus to kind of talk about. I'm trying to give you the things that are going to come up. Like obviously all the pre-calculus is fair game. I'm trying to kind of prepare you for the things you're most likely to have to see and or use in the coming weeks. So what is an even function? Well, some examples. This piece of paper is not doing it for me. That's the problem. I like writing in pen because I feel like it comes up better than pencil, but it bleeds through the paper. I feel bad. I'll use you later. Let's try that again. So some examples of even functions. Here are a couple of my favorites. F of x equal to x squared. G of x equal to cosine of x. Those are kind of my 2 favorite even functions. They're kind of the best examples of even functions. And what makes them even, well, at least visually, the way we can see that they're even is they have symmetry about the y-axis. If you were to reflect either of these graphs about the y-axis, they would look the same. Assuming I draw them not terribly. And that's kind of the defining feature of an even function. The way you tell the function's even, well, I mean, without looking at its graph, maybe it's really super terrible to graph. So it makes a function even is if f of negative x is equal to is the word that I was about to write out. That seems terrible. Why didn't I use an equal sign? Or more nicely, f of x is even. Sorry, it feels terrible. If f of negative x equals f of x. That's how we see if a function's even. On the other hand, odd functions have a different kind of symmetry. Here are 3 of my favorite odd functions. F of x equal to x cubed, g of x equal to sine of x, h of x equal to tangent of x. All those functions are odd. And if we draw them, x cubed is never my favorite to draw. Oh, okay. There's a reasonable shot at x cubed. Sine of x we've drawn already. Let's draw it again. Looks kind of like this. And tangent, I don't want to draw again. We just drew it. So all these functions have what we call rotational symmetry, meaning if you were to rotate that function 180 degrees, ow, around the origin, it would look the same. If you take this function and rotate it 180 degrees, it looks the same. This one, the same. This one, even though it seems funky, right, this part rotates over here, this part rotates over here, this part rotates itself, it looks the same. Alternatively, you could say if you reflect it in both of the axes, if you reflect this graph in the y-axis and the x-axis, they should look the same. Or this one in the y and the x-axis the same. Or alternatively, you could say the reflection in the x-axis looks the same as the reflection in the y-axis. Right? If you reflect this in the x-axis, it's the same as if you reflect it in the y-axis. Same here. I know, like, right. So the way we see that is the function is odd. Function f of x is odd if f of negative x is equal to negative f of x. I should point out, by the way, while we're here. So f of negative x is literally the reflection of your function in the y-axis. And negative f of x is the reflection in the x-axis. And same over here. Negative x is the reflection in the y-axis. So when you're writing this down, what you're literally asking yourself is the reflection in the y-axis the same as the original function? Oh yeah, it is. And here you're asking, is the reflection in the y-axis the same as the reflection in the x-axis? Oh yeah, it is. So it's a not function. And it is usually not too terrible to check, right? If we actually want to check it, it feels kind of almost silly. But if I want to check, I'm going to say, okay, well, if my function is, for example, x cubed, does f of negative x equal negative f of x? Let's see. F of negative x is negative x quantity cubed. Negative x and negative x and negative x is negative. Right, you could actually write it out. It's kind of right. No one should write this out. Whereas negative f of x is negative x cubed, which is negative x cubed. They're the same, so it's odd. So functions can be odd or even, but most of them are even. Most functions are not going to be odd or even. All trig functions are odd or even. Sine is odd, cosine is even, tangent's odd, cotangent's odd, cosecant's odd, secant's even. So the only even ones are sine and secant. I wish if I could take that back into my mouth, I would. The only even ones are cosine and secant. You know, I say the wrong thing, right? I wish to grab those words back, but they're already out there. What's that? Cosine and secant. Cosine. So we saw, well, in fact, yeah. So real quickly, if you want to see what the graphs of secant and cosecant look like. Here, so here's how I graph cosecant. I graph cosine. Sorry, here's how I graph secant. Secant, by the way, is the reciprocal of cosine. So what I'm going to do first is graph cosine. So it's 1, it's -1. Give ourselves a good old 2 pi's worth. My usual way, by the way, my usual way of graphing a trig function is going to be like going out to 2 pi, breaking it up into 4 quadrants. So I cut it in half and then cut it in half again. And then let's go out to the left as well. -2 pi, cut it in half, half, half. Those look about the same. So then cosine does this, starts here, there, there. So it kind of looks like this. I'm not really graphing it because I don't really want it. I made this a little too small. Oh well, it's just life. That's my cosine graph, more or less. So here's the thing. Secant is the reciprocal of cosine. And reciprocal functions, not inverse functions, reciprocal functions have this kind of relationship where if one of them gets bigger, the other one gets smaller. If one of them is smaller, the other one gets bigger. So if cosine is going to get smaller, 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 secant's going to get bigger. So what happens here as we move this way, as cosine moves towards the x-axis, secant's going to move away from the x-axis. Right? Cosine got really, really close to 0. So secant, which is 1 over cosine, got really, really large. And the same sort of thing happens to the left. Right? We have another. So whenever cosine is 0, secant's going to have a vertical asymptote because you're going to have 1 over 0. And it should be symmetrical, but it didn't drop perfectly. And then the same sort of thing happens down here. I should have said the reciprocal of 1 is 1. 1 over 1 still 1. What's the reciprocal of negative 1? 1. So secant of this pi is also negative 1. And then as cosine gets closer to 0, secant gets further away from 0. Okay. That's my tried and true technique for graphing secant and cosecant, drawing the reciprocal function, and then kind of just the words I use in my head are I like to flip it away from the x-axis. So I think of cosine as being kind of centered on the x-axis, and secant kind of says, oh, take those things and go away from the x-axis. Oh, sorry, like that. So there's our graph of secant.
Secant also derived from the reciprocal.
I mean, yes, in that all things are for trigonometry, but really, I mean, like I'm using the values, but I'm taking the reciprocals. So I know that cosine is, I mean, there are graphical ways of doing it that are not really what I'm thinking of. I'm just thinking of taking the values of cosine and finding their reciprocals.
So does it make sense geometrically? Like how would we visualize? So cosine is the x, y,
right.
Sine and tangent.
There, I'm not so good with the geometry of the secant function in the unit circle. I believe there is a way to make that kind of make sense. That is not what I am thinking of when I do it, but I know that there's like I know there's some sort of like, if you like on the unit circle, like if you draw some vertical line at the 1, 0 point and then draw the line connecting things, you can find the secant as like some length of a thing.
But it's not supposed to be as intuitive.
I definitely don't find it as intuitive. Yeah. I'm just thinking of taking the x value and taking the reciprocal of it. And then you could do a similar thing for cosecant. In fact, I think you all should right now. No, you want to do it? Yeah, draw cosecant. Which is the reciprocal of sine. So I would encourage you all to start with sine and then flip it away. You guys on Zoom too? I was going to look at you too. Oh, yes. Wow, those are not my straightest lines. So wherever sine is 0, you're going to get a vertical asymptote for cosecant. And then again, we're just taking this, I'm taking this value here and going up, up, and away. Or this value here and going down, down, and away. Same deal over here. Wow, these I've drawn better graphs. So I will point out my drawings are usually a little better than that, but not always excellent. Desmos is an excellent tool to see what things look like nicely. Also, you probably have purchased the book in some way, shape, or form. It is not inexpensive, as I imagine you're aware, but it has some great pictures. It also has like other useful stuff, but the pictures are really good. So I really, really encourage you to look at the book, if for nothing else than just to see the pictures, because they have some really good pictures showing you how things are really supposed to look. Sure. The other thing I'll say right now about these two graphs in particular, this is something kind of funky. It's a small thing, but I want to mention it because it's going to come up a little bit later. At some point in this class, we are going to talk about the derivatives of kind of all the functions, meaning the derivatives of power functions, exponentials, logarithms, and trig functions. Those are kind of like the 4 broad categories of functions. Also, inverse trig functions, we do talk about the derivatives briefly. Inverse secant and inverse cosecant are kind of terrible because nobody agrees what should be the choice for the domain restriction for inverse secant and cosecant. Some people, I mean, everyone, no one's wrong here. Some people think you should pick this section and this section to restrict inverse. Oh, sorry. I have a bad habit of doing that where you can't see me do it on Zoom. So let me do it over here. So some people think we should pick this section and this section to restrict the domain to for inverse secant, which is what I would probably choose because it's the same as cosine. Essentially, I mean, you're missing the middle part, but this is the same. And it's a really good choice because it's the same as cosine, but it's a really not great choice because the derivative kind of sucks. If you make this choice to restrict the domain to, the derivative of inverse secant has an absolute value in it, which nobody likes. On the other hand, if you make this choice where you pick this section and this section, like this part and this part, the derivative is nice, but the choice you've made is kind of funky. You've got this extra piece over here, and it's like, so, but some people make this choice for derivative reasons. Some people make this choice for nicer choice reasons. It's kind of weird. And really, there's literally like, some books do it this way, some books do it that way. And yeah, so you should definitely watch out. Your professor might say, we're going to define it this way. They might not even talk about it, honestly. Like sometimes these derivatives get kind of overlooked. But if they talk about the derivatives of inverse secant and inverse cosecant, make sure you pay attention to what they say because they will have to make a choice, and their choice will be what you're stuck with for that class. And then your next class will probably do a different one.
I have a question about the shape of graph for cosine and secant from 3 pi over 2 to the asymptote. So it's the graph, the actual graph, like the reciprocal, which is cosine and sine, is increasing at that period.
Sorry, which one? Sorry, we're looking at right here. No, that's pi.
All the way here to the asymptote.
So from here to there.
Yeah.
Okay.
So the actual graph, the original graph, is going upward. Going from
When you say the original graph, you mean the graph of cosine?
the
Okay.
cosine graph is going from -1 to 0.
Correct.
So it is increasing.
Correct.
How come is our graph decreasing?
Well, because it's a reciprocal. So I would say this graph is getting smaller. Even though let's talk about language here for a second. So I often, when I use the word smaller, what I often mean is not getting more negative. I mean, it's getting closer to 0. So when I think about something getting smaller, I'm thinking about getting, if it's positive, becoming less positive. If it's negative, becoming less negative, which, yes, I'm aware that means it's increasing, but it's still getting smaller in absolute value. So when I look at this, I'm like, oh, well, this function is getting smaller. It's getting smaller from the negative side. So yes, it's getting a little bit quote unquote bigger because it's getting closer to zero. But so I should be very careful about what I mean when I say things. Usually when I say smaller, I mean it's getting closer to zero. Usually when I say, so like this thing here, I would say it's getting negatively large. It is decreasing to negative infinity.
So for example, if you have just a different reciprocal value, just trying to understand the relationship there. Let's say we have, as our x, we have 3, and as our y, we have -5. And -5 is approaching 3, so approaching 0 on the x-axis.
I'm not sure what you're saying specifically here. Let me draw a picture. So you're saying,
So we have some -y, whatever it is.
okay,
On the y-axis, you have some negative value that is corresponding to some x value,
sure,
and that's approaching 0 from there to going upward to 0. So it's increasing to 0, basically in a smaller value.
sure,
And if it approaches 0, but it doesn't get to 0 because there's a vertical asymptote there.
okay,
Our reciprocal is always going to be increasing in the opposite direction, which is going to negative infinity.
right. So I would say decreasing.
Decreasing,
Right.
which is, so the graph, the slope is negative and it's going approaching negative infinity.
Yeah.
Why is that? Could you give me like an example?
Well, I mean,
so
so reciprocal functions kind of have opposite what's the word like for features, behavior. For example, if I say my function, right, if f of x is equal to x squared, it's like this. Whereas the reciprocal function, g of x equal to 1 over x squared, looks like this. So as this function, right, let's look at the right-hand side. This function is increasing from left to right, whereas its reciprocal is decreasing, which again, at least in the way I'm thinking about it, seems sensible. If the values here are getting larger, the reciprocal value should be getting smaller.
because it's 1 divided by that value.
Right, exactly. So if these values are increasing, the reciprocal values are decreasing.
Okay, that makes a little bit more sense. Seeing it in this graph makes a little bit more sense because it's just 1 being divided to more and more and more values, so it becomes smaller.
Right.
As it gets, but it doesn't reach 0.
Right. We never get to 0 here because well, we have a fraction, a rational expression, and the rational expression can only ever equal 0 if the numerator happens to be 0. Right? We have 1 divided by a larger number that is getting closer and closer to 0, but we're never actually getting there. I would point out, because why wouldn't I? This graph does have a horizontal asymptote of y equal to 0. Meaning that the graph gets super duper close to that, but doesn't actually ever get to that value. Actually, I shouldn't even really say the second part. I should really only say the first part. So really, yeah, we might as well. We're going to be there in a week anyway. When I say this, what I really mean is the following. The limit, I feel like limits, maybe let's not go there quite yet. What I really want to say is, as x gets really, really large, y gets closer and closer to 0. Or in this graph, as x gets really negatively large, y gets closer and closer to 0. And yes, I might as well. What I do mean here is the limit as x goes to infinity of this function, 1 over x squared, is 0. We're going to go talk about limits, I imagine, tomorrow, next week, soon enough. But we're pre-calculating, so I should not quite say all the limit things just yet. Tuesday will be limits abound. Yeah, let's talk about some domain and range stuff. Mostly domain. So let's say, yeah, let's talk about domain for a minute. There are 3 things to know about domain, in my opinion. Let's go this way. Let's say we have the function f of x equal to 1 over x squared plus 9x. What's the domain of that function? And really, when I ask what's in the domain, the question that I actually want to answer is what's not in the domain? Because that's usually the easier question to answer. So typically the answer is everything except for these few things. So in this particular example, there's an issue. We don't want to be dividing, not we don't want to be, we can't, right? Division by 0 doesn't work. In fact, let's make sure everyone's super clear with that just for 1 second. 5 divided by 0. Let's see here. How many times is 0 go into 5? Let's try 7. 7 times 0 is 0. 5 minus 0 is 5. Right. I mean, obviously, I'm kidding around a little bit, but the point is, right, no matter how big you make that number, right, you're never going to get the division to work out where you have a 0 remainder. Right. So 5 divided by 0 is undefined. And it's undefined in an infinite sort of way, right? If you have 5 divided by 0, it's because really what we're thinking of is we're thinking of this number being kind of very close to 0, but not actually 0. It's getting super duper large. On the other hand, just to make it extra clear, what's 0 divided by 0? Exactly. Now, I want to point out, it doesn't exist as well, but it's a kind of different kind of not existent. Let's check it out. 0 divided by 0, I was going to do it the long way. I think 7 works. So 7 times 0 is 0. 0 minus 0 is, oh, look, it worked. It worked, right? When you do division, the goal is to get a 0 remainder, right? But you might notice I could have picked anything, right? I could have picked 7. I could have picked 7 billion, and that still would have produced the same result. So the difference here is that this doesn't work at all. So it's undefined, and usually it's some sort of infinity. On the other hand, this works all too well. This works all the time. You could pick literally any value and have 0 divided by 0 equal that value. In fact, that's what we're going to see when we deal with a lot of limits, is that 0 divided by 0 isn't so much undefined, it's that it's indeterminate. Meaning it literally could be any real value. Something important to keep in mind when we're talking about limits, because you're going to see a lot of 0 over 0 types of limits, and usually your job is going to be to figure out what particular value that 0 over 0 limit actually takes on. That's right. We ended 1150. Not. Oh, stop trying to do things. Okay. So we'll finish up this domain discussion, and then that clock is a little fast. My watch says 11:39. That says 11:40 something. Okay. Let's talk about domain. So here we can't divide by 0, as I have made hopefully very clear. So we're going to exclude where that denominator is equal to 0. I'm going to factor out x times x plus 9. So either x doesn't want to be 0 or x doesn't want to be -9. So writing the domain, not my favorite. I like to draw the number line. There's -9, there's 0. I don't want those. I do want everything else. So we have to write it in this. I mean, you can write it a couple different ways. Usually the way people write domain is using interval notation. So everything from -infinity to -9 exclusive, union everything from -9 to 0 exclusive, union everything from 0 to infinity. So typically, if your issue is dividing by 0, you're just kind of pulling out a few points that make you divide by 0 and getting the entire rest of the number. On the other hand, the other two types of domain issues have slightly different types of domain restrictions. You could say, what's the domain of f of x equal to, let's make it not terrible, the square root of 6 minus 3x. Not terrible. So for division by 0, we exclude the things before we don't have 0, but if taking a square root or any even root, what kind of numbers can't we take the square root of? Negative numbers. I should say, what kind of numbers can we not take the square root of and get a real result? Because you can't take the square root of a negative and get an imaginary number, which is something we don't really get into in this class, but is something to be aware of. So yeah, we want to say, well, in this case, that 6 minus 3x has to be non-negative, greater than or equal to 0. And then you can solve this inequality in whatever way you like. My personal preference is to not have to deal with multiplying or dividing by a negative. So I would rather just add 3x over to both sides and say 6 is bigger than or equal to 3x, and then divide by positive 3. Say the 2 is bigger than or equal to x. If you don't like that, you can also do this. Negative 3x is bigger than or equal to negative 6, and then divide both sides by negative 3 and get x less than or equal to positive 2. Because when you divide and multiply by a negative, you have to change the direction of the inequality. So either way, we've got the same thing. It's just written differently. 2 is bigger than or equal to x, or x is less than or equal to 2. Means the same thing. So that's going to be, let's see, I want x to be less. You can also check a number, right? If you're like not sure which side you want. If I check 3, oh, 3 doesn't work. I don't want that side. I check 1, 1 works. I want that side. So there's my domain. So here my domain would be everything left of and including 2. What time have I got? Okay. And then the last normal type of function with domain issues, normal being relative, logarithms. Well, logarithms, I could spend an hour talking about logarithms, but I don't have an hour, so I won't. But let me, before we talk about the logarithm thing, here's my favorite logarithm thing to remember. What's log base 2 of these? Well, here's what I remember learning logarithms the first time and really struggling with them. They can be challenging in my opinion. Here's what I would really strongly recommend for you to think about when you think about a logarithm. Log base 2 of 8 just means 2 raised to what power is equal to 8. That's all a logarithm is asking for. It's asking for what exponent do I need to get from that base to that result. So what do you raise 2 to get 8? Right, 2 to the third equals 8. So I like to remind myself, if I'm ever thinking about logarithms, that this statement is equivalent to the exponential statement 2 to the third power equals 8. That is my primo logarithm. Can I say the word? No. That is my favorite logarithm thing to remember that those two go back for. More generally, it's log base b of y is equal to x corresponds to b to the x equals y. Often when I'm looking at something like this and being like, oh, b to the power of equals, that's really, when I'm looking at the logarithm, those are the things I'm seeing, like they're just there. I'm like, oh yeah, dot raised to that equals that. Some people will say these words. They used to not make very much sense to me, but they, a logarithm is an exponent. It kind of feels weird to say it that way, but it really is true. The logarithm is the exponent. What exponent? The exponent that you raise the base to get the number that's in there. So that said, we can't take the log of 0, right? If I tried to find log base 2 of 0 equal to x, what I would really be saying was 2 to the x power is equal to 0. But that doesn't work. You can't ever have 2 to the x power equal to 0. Why not? Like, couldn't they pick a really, like, what's like 2 to the, what would do like 2 to the negative 1,000? It's pretty small, right? Is it small? Or is it big? I think it's small. Let's see. Let's rewrite it as 1 over 2 to the positive. Oh, yeah, that's a very small. Because 2 to the 1,000 is too big for my calculator, I think. It's really, really big. And 1 over it is very, very small. So the problem here is that even though this is really, really, really small, it's not 0. It might literally show up as 0 if you put it into a calculator because it's like too small to be anything else that will approximate. But it is not 0. And in fact, this can never equal 0. You can't take a log of 0. And in a similar way, you can't take a log of a negative number. Because again, your base, and I should clarify, when you talk about logarithms, the bases should be positive. We don't ever have a negative base for a logarithm. That's just not something that we do. In the same way, we don't ever have a negative base for an exponential function because of problems. And I don't have the time right now to talk about all the if, ands, wheres, and whys, but I will say those things. We'll talk about it next time. Your bases for logarithms for y equal to log base b of x, and for y equal to b to the x. Inverse functions, by the way. These functions, the base had better be greater than 0 and also not equal to 1. Because otherwise there's problems. Yeah. Again, I would say more, but time. So yeah. For example, if I wanted to find the domain of something like f of x equal to the log base 7 of x squared minus 5x minus 6, I would say, well, I know I can't take the log of 0 or a negative number. So all of that stuff, all of the argument of the logarithm there has to be strictly 0. And then we're solving nonlinear inequalities. You kind of are stuck with having to factor. Right? There's really, if it's just something like 3x minus 6 or whatever the other one was, you can solve for x straight away. But if you've got powers of x that are other than 1, you usually have to do some factoring. This one does factor. Ooh, how does it factor? Is it 6 and 1 or is it 2 and 3? I think it's 6 and, well, specifically, I should say it's negative 6 and positive 1 is how it factors. So then the important numbers are x equal to 6 makes it 0, x equal to negative 1 makes it 0. You throw those on the number line. And then we say, okay, so let's see. If I pick a number bigger than 6, like 70 billion, and I plug it in, 70 billion minus 6 is positive, 70 billion plus 1 is positive, and the positive plus positive is positive. And then pick something between negative 1 and 6. Or you can do the thing where you just change the signs because you know that you have odd powers here. And the signs change here, you have odd powers. I could use another hour. I'm sure you guys, right? You definitely want to stay for another hour. I understand you probably mathed out for the moment. But if you pick a number between negative 1 and 6, like 0, negative times positive, and then something over here, like negative 2, negative 8, minus 1, positive, negative times negative. And we want it to be positive, so we pick these sections. We don't pick this. We don't want those points either because they make it equal to 0. So here our domain would be everything from negative infinity to negative 1, union everything from 6 to infinity. So here's the breakdown for what I'll say about domain. For domain, there are 3 things to consider. If your function looks like I don't care over some stuff, we want to say that the stuff needs to be not equal to 0. If your function looks like the square root of some stuff, or really any even root, right? It could be a 4th root, a 6th root, a 7th, not a 7th root. Odd roots are fine. You can totally take a cube root of a negative number. What's the cube root of negative 8? Right, because negative 2 times negative 2 times negative 2 is negative 8. So odd roots have domain everything. Even roots, you can't take even roots of negative numbers. So here you have the square root of stuff or stuff to say like the 1/4 power, because that's the same as the 4th root. Our stuff has to be non-negative. And finally, if your function is a logarithm of some stuff, that stuff has to be strictly positive. Those are the main rules for finding domains of functions.